This is the physics flipped classroom video on vaporizers and inhaled anesthetics. This is the material that will be covered both in this video as well as in your in-class session from the ABA Basic Content Outline. We will go through gas laws, vaporizers, anesthetic uptake, the concentration effect, the second gas effect, and nitrous oxide. We'll start with the gas laws. So when a volatile liquid is in a closed container, the molecules will move from the liquid phase to the vapor phase until the number of molecules in the vapor phase is constant. The molecules in the vapor phase will bombard the walls of the container, creating a pressure. And this is called the vapor pressure. The vapor pressure is dependent on temperature and the physical characteristics of the liquid. When temperature increases, there's an increase of molecules in the vapor phase, leading to an increase in vapor pressure. The saturated vapor pressure occurs when the gas phase contains all the vapor it can hold at a given temperature. These are the saturated vapor pressures for the main volatile agents we use. Next, we'll talk about vaporizers. Main thing I want you to get from this section is this equation for the calculation of vaporizer output. We're not going to do examples of it with the video. You'll be applying this in your in-class session. The volume of a gas exiting the vaporizer equals the volume of the carrier gas entering plus the volume of the vaporized anesthetic. So the saturated vapor pressure of the agent, examples are here, divided by the total pressure equals the agent vapor over the carrier gas plus the agent vapor. So it equals the volume of the agent vapor divided by the total volume leaving the vaporizer. The vaporizers that we use are variable bypass, flow over, agent specific, temperature compensated. The total flow of gas arriving from the anesthesia machine over here is split between the variable bypass, which will go up here, and the vaporizing chamber down here. And this is where the anesthetic agent is contained. The ratio of these two flows is a splitting ratio. The splitting ratio depends on the agent, the temperature, and the chosen vapor concentration to be delivered to the patient circuit. Now most of our vaporizers are flow over, and this means that the gas is channeled through the vaporizing chamber and it flows over a wick system. These would be the wicks, and they're saturated with liquid anesthesia. And so the vapor also becomes saturated with this anesthetic. Now the flow over method of vaporization is in contrast with the bubble through method, which is used for the copper kettle system. When vapor is generated, it takes heat from the liquid and its surroundings, and so that heat energy is lost. When that heat energy is lost, the temperature of the vaporizer and liquid decreases, which decreases the vapor pressure of the anesthetic, which decreases the vaporizer output unless a compensatory mechanism occurs. And that's what this temperature method does. So there are multiple mechanisms in vaporizers to correct for temperature. This one is the bimetallic strips. There's a different coefficient of expansion for each strip, for, in this example, the green and the red. As temperature rises, one surface expands more than the other, so the green one. So this strip is attached to a flap that diverts gas through either the bypass or the vaporizing chamber in order to maintain a constant concentration output. There are multiple factors that influence vaporizer output, and these include altitude, flow rate, intermittent back pressure, and carrier gas composition. So low flow rates, which we're going to define as less than 250 mLs per minute, decrease the amount of output compared to what you have dialed in. The volatile anesthetics have a relatively high density. At low flow rates, there's insufficient turbulence generated in the vaporizing chamber to upwardly advance the vapor molecules. At high flow rates, which we're going to call 15 liters per minute, you also have a decreased output as compared to what you dialed in. And that's because there is incomplete mixing and failure to saturate the carrier gas in the vaporizer chamber. Intermittent back pressure increases the vaporizer output. So back pressure is suddenly released during exhalation or expiration of positive pressure ventilation. The vapor exits the vaporizing chamber via both the vaporizing chamber outlet and retrograde through the vaporizing chamber inlet. The output resistance of the bypass chamber is lower than that of the vaporizing chamber. Carrier gas composition, mainly switching from oxygen to nitrous oxide, also affects output. Nitrous oxide is more soluble in volatile anesthetics, which decreases the vaporizer output. When the volatile anesthetic is saturated, you have an increase in output until a new steady state is reached. And it is unclear why you move to this new steady state. There are multiple potential hazards with vaporizers. One is misfilling. With this, you can give either too much or too little anesthetic. And the safety check to prevent this is by having a key device to fill the vaporizers that's specific to the agent and the vaporizer. Tipping can cause agent to enter the bypass chamber, which leading to an output with an extremely high agent concentration. You can avoid this by either attaching the vaporizer to the machine during transport or by putting the vaporizer into the transport dial setting when you move it. Overfilling causes liquid anesthetic to enter the bypass chamber and increase agent output. Underfilling decreases agent output. Simultaneous inhaled anesthetic administration is pretty much avoided now because we have the safety feature of the interlock system, which prevents you from turning on multiple vaporizers at the same time. Leaks will decrease agent output. To check this, you should do the negative pressure leak test every morning when you start your cases, before you start your cases. The Tech 6 is the vaporizer for desflooring, and this one is special. It's electrically heated, thermostatically controlled, at a constant temperature, pressurized, and it's a dual gas blender. Next, we're going to talk about anesthetic uptake. You have an increased FA to FI, or alveolar gas concentration to inspired gas concentration, leads to a faster induction. So this ratio increases with increased fresh gas flows, increased volatile anesthetic concentration, decreased blood gas solubility, increased minute ventilation, decreased cardiac output, which is more pronounced with the more soluble agents, and increased pulmonary arterial and venous blood partial pressures. High alveolar ventilation relative to uptake from the lungs to the bloodstream generates the initial high slope of these curves. At the beginning of induction, the venous partial pressure is 0 but rises rapidly, and the FA to FI ratio increases rapidly. Later during induction and maintenance, the venous blood partial pressure rises more slowly, so the FA to FI rises more slowly. The knee in the curve of these lines reflects the speed at which FA equilibrates with FI. The greater the uptake into the blood, or more soluble, the slower the rate of rise. So transfer of volatile anesthetic from the anesthetic machine to the alveoli is dependent on the inspired partial pressure, alveolar ventilation, and characteristics of the circuit, as far as how much the agent sticks to the circuit. Transfer of volatile anesthetic from the alveoli to the arterial blood is dependent on blood gas partition coefficient, cardiac output, alveolar to venous partial pressure difference, and transfer of volatile anesthetic from the arterial blood to the brain is dependent on brain blood partition coefficient, cerebral blood flow, and arterial to venous partial pressure differences. Moving on to the concentration effect. Consider the administration of 10% anesthetic, so 10 parts anesthetic, here in the blue, and 90 parts of other gas, to a patient in whom 50% of the anesthetic in the alveoli is absorbed by the blood. So 50% of the anesthetic is absorbed in the blood, which is 5 parts in the blood, 5 parts in the alveoli. In this case, 5 parts of the anesthetic remain in the alveoli, and 5 parts enter the blood, and 90 parts remain as other alveolar gas. The alveolar concentration is now 5.3%. Now consider the administration of 50% anesthetic with the same 50% uptake. But now you have 25 parts of anesthetic remaining in the alveoli and 25 parts that pass into the blood, and 50 parts remain as other alveolar gas. So here the alveolar concentration is 33%, giving 5 times as much anesthetic has led to a 6.2 times greater increase in alveolar concentration. The higher the Fi, the greater this effect. Now with augmented gas inflow, you still have the 50% anesthetic and 50% uptake, and the 25 parts of the anesthetic was removed from the alveoli here, and they're replaced with 25 parts of the 50% anesthetic, giving a new alveolar concentration of 37.5% as compared to 33% without augmented inflow. Thus, 5 times the Fi leads to 6.8 times greater Fa compared to 6.2 times without augmented gas inflow. Of course, this cycle of absorbed gas being replaced by fresh gas inflow is continuous and has a finite rate. So our example is a simplification. Next, we'll talk about the second gas effect. And this is when there's a potent anesthetic combined with nitrous oxide. So consider administering 2% of a potent anesthetic in 70% nitrous oxide and 28% oxygen. In this case, nitrous oxide, with its extremely high partial pressure, despite low solubility, partitions into the blood more rapidly than the potent anesthetic, decreasing the alveolar nitrous oxide concentration by some amount. Let's say for this example 50%. Ignoring uptake of the potent anesthetic, the uptake of nitrous oxide is 35 parts, leaving 35 parts nitrous oxide, 28 parts of oxygen, and 2 parts of the potent agent in the alveoli. So the anesthetic gas is now present in the alveoli at a concentration of 3.1%, up from 2%. So the potent agent has been concentrated and Fa has increased. Lastly, we'll talk about nitrous oxide. So the blood gas partition coefficient of nitrous oxide is 34 times that of nitrogen. So when nitrous oxide leaves blood and enters the air-filled space, 34 times faster than nitrogen leaves the cavity to enter the blood. So this leads to either increase in volume or pressure depending on the nature of the cavity. As far as clinical relevance, you want to be cautious and possibly avoid nitrous oxide in instances where you can have this increase in volume or increase in pressure in a specific space. So be cautious with areas of intestinal gas, pneumothorax, pulmonary blebs, potential air embolism, middle ear operations, cerebral ventricles, and the supratentorial subdural space. So we went through gas laws, vaporizers, anesthetic uptake, the concentration effect, second gas effect, and nitrous oxide. Thank you.